Good morning, students. Till the last lecture that you have attended, you must have gone through the chemical properties of haloalkanes. Let us have a small recap of the chemical properties. The first property that you studied in the part of haloalkane is nucleophilic substitution. In the last lecture, you were told about the mechanism SN2, SN1, and how the feasibility of these mechanisms takes place. So, the nucleophilic substitution that you attended in the previous lecture. The second, elimination reaction that occurs in presence of alcoholic KOH. Very important reaction, also known as beta elimination reaction. Beta elimination, because the hydrogen that we are removing is from the beta position. Now, in today's lecture, what we are going to start is the third type of chemical property of haloalkane, that is reaction with metals. A small recap of the property regarding the metal was in class 11th, also known by the name of the Woods reaction. So, in today's topic, what we are going to do, we are dealing with the third chemical property of haloalkane, that is reaction with metal. We are going to do simultaneously the two metals that we are going to do. One is sodium and the other is magnesium. Sodium and magnesium, the two metals which are going to take part in the reaction with the haloalkane. These compounds are also known by the name of organometallic compounds. So a very sincere approach towards it is organo related to carbon and metal part. So when we are dealing with Rx related with Na or Rx related with Mg, it gives rise to the type of compound, mainly in case of Mg, as organometallic compounds. So, starting with the third topic of today's lecture, the third part, reaction with the metals. Follow NCERT simultaneously, very important in CBSE. The third heading of the continued part is with metals. We are going to do simultaneously some NCERT questions also. The first metal that we will be dealing with is sodium. Now, the reaction start is RS, haloalkane, react with sodium, another molecule of haloalkane. We will be showing the simultaneous removal in presence of dry ether. A number of times what happens is the teacher is not writing dry ether, they are writing ROR. So don't get confused, ethers are also represented as ROR. So what you are getting now is R bond R plus 2NaX. Now the thing that we used to make you memorize in class 11, the most important part is that Woods reaction is applicable only in case of when we are going to get alkane with even number of carbon atom. Even number of carbons. So, because the number is going to double, when it is going to double is always going to be an even number. So, if in our mind the question arises how to get propane using the Woods reaction, this reaction is Woods reaction. So if we are going to produce propane by using Woods reaction, would it be feasible or not? Let's have a look of it. For example, for propane, let us take prop 3 carbon. So one of the haloalkane must be of 1 carbon and the other haloalkane must be of 2 carbon. So the next one must be C2H5. On paper we used to draw that we are getting, what we are getting is propane. But actually, it is not at all fixed that we will only get propane, because in the reaction mixture there are number of halomethanes, there are number of haloethanes. So the product can be varied. It can also be CH3 bond CH3, that is ethane. It can also be C2H5 bond C2H5. So what we are getting, in spite of getting the single answer, we are getting number of products, large number of products, and separation becomes difficult because all of are having a homologous series attached to them. So the separation becomes difficult. Now the other related question to it. The first is the alkane with even number of carbon can only be obtained. The reaction is not applicable in case of odd number of carbon atoms. Now the second very important question. The reaction can be asked for R and R dash. So you are going to write it as not possible, because R dash are both the R must be same. Both the R must be same. They cannot be taken as R and R dash. Now let's move to the other metal. The other metal is Mg, magnesium. Magnesium reacts with haloalkane. Magnesium reacts with haloalkane and we are going to get the organometallic compound. The other metal is Mg. Rx with Mg. Now, what happened? What we are going to get is RMgX, alkyl magnesium halide, also known by the name of Grignard's reagent. A very important reagent going to produce large number of organic compounds. In the further sessions you are going to study how the Grignard reagent produce large number of organic compounds. But now the two things that we should be must knowing over here is R, Mg, X. Mg is the metal. Mg and X is electronegative in nature. So the electronegative sign arises over the halogen atom. Side by side, magnesium metal, this time is electropositive. With X it is always electropositive. This part gives us about the ionic character. But what about R and Mg? It is slightly covalent in nature, and here this R is electronegative as compared to Mg. So the structure, how the charges arise in case of Grignard reagent should be very clear, that which is electropositive and which is electronegative in nature, and which part of the bond is ionic and which part of the bond is covalent in nature. Now the second very important question, a part of our NCERT back exercise, that Grignard reagent should always be kept in anhydrous condition. Anhydrous, that is without water. It should always be kept anhydrous. So number of times what the answer we find in the copies is because Grignard reagent react with water. But what happens when it reacts with water? The question itself is saying it should be kept anhydrous. So very simple thing, that it must be reacting with water. But chemically what happens when it reacts with water? So let's have a look. When RMgX, that is Grignard reagent, comes in presence of any of the protic solvent, that is which is going to provide a proton, a protic solvent, what happens to it? It donates a proton, it gives the proton to the R part. What we get here is RH along with Mg known as alkane. So why Grignard reagent should be kept anhydrous? Grignard reagent should be kept anhydrous because otherwise it would react with water, a protic solvent, which would give H, a proton, to the R part, forming alkane along with magnesium hydroxy halide. So in spite of getting the Grignard reagent, we will be getting alkane as the product. So these are the chemical properties related with the metal part. So what we did is, in the chemical properties of haloalkane, the first nucleophilic substitution, second elimination reaction, the beta elimination where we have deal with the Sirzoff rule, and the third is reaction with metal. Metal is Mg and Na. In case of Na, we are following the Woods reaction, and in case of Mg, we are going to get the Grignard reagent. So the two questions are the structure of Grignard reagent, where the electropositive and electronegative character lies, and the second, why Grignard reagent should be kept anhydrous. So this is the part of chemical properties of haloalkane. Then further we will move towards the chemical properties of haloarene. But before doing that part, let's have a look of some of the questions, very important questions of CBSE. We will be doing simultaneously the questions also, so that the topic becomes more clear to you. It is compulsory to do the intake, salt and the back exercise simultaneously when you are going along with the topic. So it is one of the index question. In this part, we have to identify what are the unknown things here. So first of all, I am plotting the question here. Plus Mg So, in the meantime, try to find out what the answers must be here. D2CH3 In the CBSE, such type of questions are very common to identify A, B, C, D, and usually each of these parts carries half mark. The identification of each of these parts carries half marks. The student must be having the knowledge of this topic. And we have to simultaneously judge what are A, B, C, D. The following things must be simultaneously judged. Okay, what we have to determine here is, I am encircling those parts which we have to determine. So what we are going to do is, we are going to find out A, B, C, D, E, R dash and R. Okay, revising the topic. Br with Mg, carbon, Br, Mg. The topic we have studied just now is Grignard reagent. What A must be? What A must be? It must be cyclohexyl part, Mg, and then Br, the Grignard reagent. So identified A, very simple. We are following the rules of Grignard reagent. How the Grignard reagent is prepared? When haloalkene part react with the Mg, we get the Grignard reagent. But the simultaneous condition, what we remember is that Grignard reagent should be kept anhydrous. Otherwise, the proton donor would give H and would result in formation of alkane. So what B must be? B must be the cyclohexane part. And what is the part released? Mg, OH, and then Br. So determine A and B. NCERT question, determine A Grignard reagent. But students, now here we have to determine R also. So with the following part, the R value can be determined from here. A number of times what the student think, as we have to determine D also, they move to this D part. But students, H2O is water and D, remembering it is deuterium, heavy water. Whatever the thing, the proton donor is going to donate the proton, and in this case, D2O is going to give D to the R part. As water is giving H to this part, D2O is giving D to this part. So what we get? R, D. As before we used to get R, H. In this case, what we will be getting? R, D. So it must be R and D. Can you then now find out what the value of R must be? R must be this part. What this part is known as? It is isopropyl. Isopropyl. R must be equivalent to isopropyl. This must be Grignard reagent. So what is this? What is the value of R? R is Grignard reagent. R is isopropyl bromide. Don't forget to put the equivalent value of H on each of these carbon atoms. So R, isopropyl, Br reacts with Mg to give R, Mg, Br. So what is the formula of C? CH3, CCH3, Mg, Br. So determine the value of R also. Now, we have determined A, B, R, isopropyl part, C, the complete structure, and R from here also. So let us come to the third part of this, R dash X. Look at this part. This part is having arrow on the right as well as on the left, on both the sides, on right as well as the left. So don't try to start the reactions from here. Look at the reactant part and move accordingly. R dash X in presence of sodium and ether. Sodium and ether is going to give, sodium and ether make us remember of which reaction? Which reaction we are going to point out from here? It is Woods. And what is the main feature of Woods reaction? That it is going to double the number of alkyl carbons. It makes the alkyl carbon double. So if it is a double structure, then what is the value of R dash? Let us divide the whole of the structure into two parts. Because Woods gave the double structure, so we will divide it into two parts to get the R dash part. So R dash must be CH3, 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 and that is X. What is R dash now? It is tert butyl. The center is carbon. It is tert butyl halide. How we came to know it as R dash is tert butyl? Because this reaction shows sodium and ether, which is making us remember about the Woods reaction, and Woods make the carbon atom double. Now this part, R dash X reacts with Mg. Mg, the reaction gives us, make us remember of the Grignard reagent. So D must be R dash Mg X. R dash Mg X. So let us substitute the value of R dash. Tert butyl part. The tert butyl part. CH3, 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 Mg X. Getting my point that it is, since R dash is tert butyl, so tert butyl halide on reaction with Mg would be giving us the simultaneous Grignard reagent. Now again they have shown water. And what happens when Grignard reagent reacts with water? Water gives a proton to the Grignard reagent, forming the simultaneous alkane. So all the reactions are going with the same sequence again and again, that Grignard reagent should be kept anhydrous. So simultaneously we determine A, B, C, R, isopropyl part, R dash, third butyl part, D, third butyl magnesium halide, and what is E? E, the simple alkane. It is one of the question that was given in CBSE 12, and usually each of these part A, B, C, D, they carry half marks each. And if you determine any of the part wrong, so this is stepwise marking, so the marks of only that part will be deducted. So please try to follow the Woods and Grignard and what happens when Grignard react with water. The full question related to reaction with metals. So you must have gone through this topic. Let's move towards the chemical properties of haloarenes. Haloarenes. Must do NCERT question as we are going further in the lecture. Simultaneously open your NCERT, tick the topics, read each and every line of NCERT because the objective part will be carrying these topics again and again. So the next topic here is chemical properties of haloarenes. There are three important properties of haloarenes as the three important properties in case of haloalkane. So have a look of, we will simultaneously do the things making the comparison in between haloalkane and haloarene. But the three things that you did in haloalkane, the three chemical properties were nucleophilic substitution. The second property that you did there was elimination reaction, beta elimination. And the third property was reaction with metal, that is sodium and magnesium. Now let us do simultaneous the part in case of haloarenes. In case of haloarenes, the first property already explained to you in the previous lecture, but has a slight look of it. The first is nucleophilic substitution. Now the question arises whether haloalkane and haloarene equally feasible for the nucleophilic substitution or not, because haloarenes are a resonance stabilized part. Okay, so let's have a look. Let us take an example of chlorobenzene. Although this topic was explained to you in the previous lesson, but moving to the chemical properties, have a small remembrance of this topic. The haloarenes are very less reactive towards the nucleophilic substitution, and a question arises here. Usually this question is of 2 marks and we have to give the 4 points why haloarenes are not able to undergo or are less reactive for the nucleophilic substitution. So the 4 important things. First, these are resonance stabilized group. Chlorine, a deactivating group. Although it is ortho-para directing, but since Cl is minus I, a minus I group, it is deactivating in nature. Second, due to resonance stability, it is not allowing chlorine to get substituted by any other nucleophile. The second case, the carbon halogen bond in case of haloalkane, it is single bond character. It is single bond character. But in case of haloarene, it has partial double bond character. What is partial double bond character? When we draw the resonance of chlorobenzene, during the resonating step, the plus R effect, the single bond which was attached in between Cl and C gets a partial double bond character. We will be drawing the resonance here also. The third part, the carbon with X in case of haloalkane is sp3 hybridized, but the carbon related to X in case of haloarene is sp2 hybridized. It is haloarene and it is haloalkane. The instability of phenyl carbocation. If we make it remove Cl, remove from it, and we get the phenyl carbocation, it is unstable. Instability of phenyl carbocation. And a nucleophile is negative in nature. It is rich with electron. In case of conjugation, when we are talking about the halobenzene, there are 3 pi bonds having a large number of electron density moving above and below the plane. When the nucleophile attacks over it, tries to substitute it, then the electron-electron repulsion is also there in between these pi electron cloud and the electrons of the nucleophile. So electronic repulsion also arises, so it becomes difficult that in normal condition that we will be getting substituted Cl by the nucleophile. But there are certain vigorous conditions also in which we remove the Cl with the OH. One of the conditions is 623 Kelvin and 300 atmosphere. It is the main condition in which the Cl gets substituted by OH. So I am writing here is the vigorous condition, Cl gets substituted by OH. Although we are telling that Cl cannot be substituted, there are less reactivity of haloarenes for the nucleophilic substitution. But must remember the condition 623 Kelvin, 300 atmosphere in presence of NaOH and HCl, you will get directly what? The phenol. Benzene with the OH, phenol. The reaction becomes easier if these ortho-para places we put NO2, because NO2 is electron withdrawing group. It will decrease the electron density over it, and due to decrease in electron density, the nucleophilic attack would become easier. So the main thing is, in normal condition the Cl cannot be substituted, but in vigorous condition, that is 623 Kelvin, 300 atmosphere, NaOH and HCl, it can be substituted, giving rise to phenol. But if we want that the condition should be mild and milder, then we have to block these ortho and para positions, because these positions are rich with the electrons. So the nucleophiles get a lot of repulsion from these positions. So blocking these positions makes the nucleophilic attack easier. So this was the first property of nucleophilic substitution. Now the second property. Must revise this. This question was of 2 marks in CBSE, that we have to give 4 points why the nucleophilic substitution is less in case of haloarenes. So moving to the second part, second type of chemical property of the haloarenes. The second property is electrophilic substitution in haloarene. This is the second chemical property of haloarenes. Electrophile, E positive, a species which is having less electron, which is in search of electron. And we all know that in case of haloarenes, the electron density is high on ortho and para position. So, what do you think? The electrophile will be attacking on which position? So, the answer comes to your mind is on those positions where the electron density is large. And the electron density is large on which positions? Ortho and para. So, let's have a look how the ortho and para positions are rich in electron, drawing the resonating structure. chlorobenzene, 3 electron pairs. Let's start with the resonance part. A pair of electron becomes a bond. Let's have a look that it is going to give rise to the partial double bond character. Partial double bond character. As soon as this bond rotates here, this bond comes to the corner position. Lone pair is converted into a bond, and a bond is converted into a lone pair to balance the overall structure. So what you are going to get? Now here it is double bond. This Cl, how many electrons are left? 4. Giving the electron, it is getting the positive charge, and getting the pair of electron, negative charge. So this carbon is now not having the complete part over it. 1 bond, 2 bond, and on the one side it is H. Benzene ring is having H on the carbons. So in order to make it stable, 4 bonds, it converts the lone pair into bond. As soon as the lone pair is converted into bond, this carbon, double, and 1 H. What the valency becomes for it? What the number of bonds? How many bonds are there? It is 5. So carbon is having 4 bonds. So it will make shift of this pi bond into the electron pair on the para position. Let's draw the other structure. Negative charge, because the bond has been shifted on the para position. Partial double bond character. Now you are able to visualize what the word I used is partial double bond character. Although the Cl with carbon is a single bond character, but during the resonance it gets the partial double bond character. Now this carbon again having the 3 bonds, 1, 2 and the H. Bond line structure is this. The electron pair is converted into a bond. Simultaneously a bond is converted into electron pair. So what the next structure is? Negative, rich electron, double bond. All the other things will remain the same. Now what happened to the ortho position? Now the ortho position is having 3 bonds. In order to make it with the 4 bond character, again the shifting of the lone pair into a pi bond, and this pi bond goes back to its original position. So number of times students are what the thing we are doing, we are making the things as before. There is no difference in the first and last structure. A number of times the student asks that there is no difference. What we are doing is we are rotating the electrons here and there. But this rotation of electron is actually the delocalization. Delocalization giving rise to the resonance effect. And what the resonance gives? The resonance gives the structure the stability. And when this type of resonance takes place towards the conjugated structure, this resonance is known as plus R effect. Now here we have got the 5 structures. Rotation of bonds have taken place, and the other thing that we find out over here is, the main thing that we find out over here is high electron density at which position? Ortho and para positions. High electron density, rich in electron, these are the ortho and para positions. So what do you think? Where the electrophile is going to attack? Electrophile which is in search of electrons. So where it is getting this fulfillment of electron at ortho, the para, again the ortho. So the electrophilic substitution would take place at ortho and para positions. So now we are going to make the attack of the electrophile, and we are going to get the 2 products, one at the ortho and the other at the para. Along with this topic, you must remember that in case of halobenzene, there is minus I effect of the Cl. It is taking away the electron, single bond character. Simultaneously there is a plus R effect, resonance going on in the structure as we have seen. So it gives rise to deactivating effect. Remember this, the Cl gives rise to deactivating effect because it is plus R as well as simultaneously it is minus I. Although it is ortho-para directing, it is a deactivating group. A question related with the salt example deals with this part. So let us take few examples of the electrophilic substitution. Main part, delocalization. Resonance, which type of resonance? Plus R, giving rise to high electron density at ortho and para position, and the electrophilic substitution is going to take place at ortho and para positions. So in class 11 we have gone through 5 electrophiles. Let's have a look of these 5 electrophiles on the chlorobenzene. In the meantime, let's remember what the electrophiles are. In case of haloalkanes, these are methyl, Cl, all these are the electrophiles. So the first electrophilic reaction, we have taken chlorobenzene, added Cl2 in presence of anhydrous AlCl3. Remembering AlCl3 is a Lewis acid, then what we get is, we will get one ortho and the other para product. 1,2-dichlorobenzene, 1,4-dichlorobenzene. It is ortho and it is para. Para, symmetry leads to stability, and since it is stable, it is going to be the major product and it is going to be the minor product. So halogenation using chlorine, giving it the name of chlorination. Takes place in presence of which anhydrous? AlCl3. Now the second one. Second is nitration. In the case of nitration, the electrophile is NO2 positive. We have taken chlorobenzene, then we are using the nitrating mixture. What the nitrating mixture is? Concentrated HNO3 along with H2SO4. This is known as the nitrating mixture. Then what you get is NO2 group, one at the ortho and the other at the para position. Again, remember that the para is going to be the major product. Cl is ortho-para directing. Nitration gives rise to electrophile which is NO2 positive. So NO2 is getting at ortho, NO2 is getting at para. But what the para is going to be? Para is going to be the major product because it is symmetrical. The third is sulfonation. Now the chlorobenzene is going to be substituted by the sulfonic part. Now we have taken chlorobenzene. Sulfonation. What the sulfonation part deals with is, we are going to do the questions also along with it. The sulfonation part deals with the sulfuric acid. Sulfuric acid is concentrated sulfuric acid, and we will be adding concentrated H2SO4. Heating is followed simultaneously. What we will get is Cl, SO3H, and another time Cl with SO3H sulfonic group on the para part. Remembering that the ring with SO3H group is known as benzene sulfonic acid. So what is the name given to it is ortho, the second 2-chloro, and it is the 4-chloro. I am writing with the main one. When we are having a benzene ring with SO3H, the name is benzene sulfonic acid. So we will be giving simultaneously the names 2-chloro and 4-chloro. These are the three electrophilic reactions taking part on the haloarenes: chlorination, nitration and sulfonation. Now the two other left are Friedel-Crafts alkylation and the Friedel-Crafts acylation. Friedel-Crafts, based on the electrophilic nature. These are some reactions which are always a part of each of the lesson. Now the fourth one is Friedel-Crafts alkylation, and last is the Friedel-Crafts acylation. Usually the alkylation is done by using CH3Cl. So starting with chlorobenzene, then adding CH3Cl, chloromethane in presence of anhydrous AlCl3. What we get again? In this case, the methyl is the electrophile. So we will be getting the two products. One is Cl with CH3 and the other at ortho position and the one other at para position. Okay, 2-chloro. It is the ortho-chloro and the simultaneously. The first time we are getting methyl at ortho position and the other time we are getting methyl at the para position, because chloro itself is on the benzene ring. The chlorine gives rise to ortho and para derivative. The two derivatives are there. Again, it is going to be the major part and it is going to be the minor part. Now the last one, Friedel-Crafts acylation. Friedel-Crafts acylation. So let's have a look of the acyl group. CH3COCl. This is the acyl part. A number of times what we used to take is CH3, acidic anhydride can also be taken. Here is acyl group. We are dealing with the acyl part. So acyl group, any of the group which is going to give us acyl. So the reaction takes place in presence of anhydrous AlCl3. What the two products here we are getting is the acyl group at one position on the ortho part and on the other part it is going to be at the para position. So there are the 5 types of electrophilic reaction: chlorination, then nitration, sulfonation, alkylation, Friedel-Crafts alkylation. Getting each time we are getting ortho and para, and Friedel-Crafts acylation. So the 5 electrophilic reactions. The first reaction what we did is, in case of haloarene, is nucleophilic substitution, to which it is less reactive. The second we did is electrophilic substitution taking place at ortho and para position. Now the third reaction, which was in haloalkane also, the reaction with metal. We are going to deal with the reaction with metal part now. Reaction with metal, and here also the metals are same: sodium and magnesium. Reaction with metal. Reaction with metal. Now again the two metals are, the third reactions, the two metals are sodium and the other is magnesium. Now sodium, what makes us remember about the sodium is again the Woods reaction, but the Woods name is given in case of haloalkane. So we are going to do some questions also regarding with it. In case of Woods reaction, in case of sodium, we are not going to give it the name Woods. Woods is applicable only to the haloalkane part. So taking halobenzene, chlorobenzene, 2Na, XR or CLR, we will take CLR. The same method applicable. Presence of ether, what we get is R group attached on the benzene. Now we are getting alkyl as well as the aryl part along with 2NaCl. It is having a part of the woods part. We will be giving new names for this reaction also. We are not going to call it the Woods reaction. We will simply write it here as halogen X. Now in this case I have taken both the aryl groups. The reaction is going to be in the similar manner. Removal of 2NaX. The presence is again of ether. In this case we are going to get the two aryl parts attached simultaneously. And removal is again same, 2NaX. So it is very much similar to the Woods reaction. Remembering this is very much similar to the Woods reaction. But this is not known by the name of Woods reaction. We are going to call it as Fittig reaction. This is known as the Fittig reaction. And what about this? It is having a ring, it is having the chain part. We are going to call it as Woods Fittig reaction. So again there are two name reaction. One is the Fittig reaction and both the part are the ring, and this is the Woods Fittig reaction and one is the ring and other is the alkyl part. So now let's come to the other metal. This is Mg. What happened when Rx react with Mg? Remembering, when Rx react with Mg, it is known as the Grignard reagent. So let's have a look now this time. We have taken the haloalkane part, and haloalkane part is now reacted with Mg. What we get is the Grignard reagent. The Grignard reagent, aryl magnesium halide. So the last part of this topic is chemical properties of haloarenes. Haloarenes, the reaction with metal. With sodium and with magnesium also we can do it simultaneously. In NCERT usually it is given with Na, but we can prepare Mg also in the same manner. So after this part, what we are getting is, in our syllabus is the polyhalogen compounds. In the beginning of the lesson you must be remembering that we have studied about a number of things which are a part of our daily life. The halogenes, chloramphenicol and antibiotic, but there are a number of polyhalogen compounds which are also very important in our day-to-day life. Some of these polyhalogen compounds, let's deal with some of these polyhalogen compounds. The polyhalogen compounds can be chloroform, anesthetic in the previous time it was used as the anesthetic. Polyhalogen compounds. Let's have a look of it. Polyhalogen compounds, the last part of this topic, we will be doing with it. Anesthetic and many other things are based on it. We will be doing it simultaneously. Number of things the polyhalogen compounds we are dealing is. We will be starting with it. Number of things we are going to deal with. Polyhalogen, the dichloro and many other things are there. Let's have a look at it.
Health risks and environmental problems associated with some important polyhalogen compounds. Polyhalogen compounds are carbon compounds containing more than one halogen atom. Some examples of polyhalogen compounds are shown here. Many polyhalogen compounds are useful in the industry and in agriculture. Dihaloalkane, also called methylene chloride, is a colorless volatile liquid with a moderately sweet aroma. Dihaloalkane is used as a propellant in aerosols and also as a paint remover. However, The use of dichloromethane for removing paint has been banned by the European Union, since it is a carcinogen or a cancer-causing agent. Dichloromethane is also used as a process solvent in the manufacture of drugs. It has additional uses as a metal-cleaning and finishing solvent. There are some very rare human health risks associated with exposure to dichloromethane. It harms the central nervous system. Exposure to even low levels of the air can lead to slightly impaired hearing and vision. Exposure to higher levels of the air may cause dizziness, nausea, and tingling or numbness in the fingers and toes. The skin may experience an intense burning sensation and mild redness if it comes in direct contact with dichloromethane. If dichloromethane comes in direct contact with the eyes, it may burn the cornea. Trichloromethane, or chloroform, is a colorless, volatile, non-flammable liquid with a sweet odor. It is used as a solvent for fats, alcohols, iodine, and other substances. It is also used in the synthesis of freon, a refrigerant, or R22 shown here. Many nations are phasing out the use of R22 due to concerns about its role in ozone depletion. Chloroform was once used as a general anesthetic in surgery. However, this use has been discontinued as there are a number of safer alternatives. Exposure to chloroform can cause serious problems to human health. Breathing in chloroform vapors depresses the central nervous system, not surprising considering its historical role in anesthesia. Breathing chloroform about 900 pounds per minute, even for a short time, can cause dizziness, fatigue, and headache. Chronic chloroform exposure may cause damage to the kidneys and liver. In the liver, chloroform is metabolized to form phosgene, a deadly gas. We discuss phosgene in greater detail shortly. Some people will have sources the skin comes in contact with chloroform. Chloroform is slowly oxidized by air in the presence of light into deadly phosgene gas, as shown in the reaction. Therefore, chloroform is stored in dark bottles to prevent exposure to light.
Dear students, I want to tell you here one thing, that a number of times the student get confused with the two words phosgene and phosphine. The examiner is talking about phosgene and they are giving the answer about phosphine. Phosphine is pH3, while phosgene is COCl2. So please remember this. A very rhyming word, phosgene and phosphine, but there is a lot of difference in between their structures. So these things must be kept in mind while we are studying the topic.
The bottles are filled completely to keep air out. For the sake of safety, handle every bottle of chloroform as if it contains phosgene. Wear gloves and eye protection. There are several tests that you can carry out to determine the presence of phosgene. Phosgene, or carbonyl chloride, has a characteristic odor of cut hay. It is highly toxic. In fact, it was used as a chemical warfare agent during the First World War. If you detect the odor of freshly cut hay when working with chloroform, you should seek medical attention. Chloroform contaminated by phosgene should not be used and should be properly disposed of as chemical waste. or iodoform, is a very yellow crystalline solid. This volatile compound has a pungent, medicine-like odor. Iodoform has uses as an antiseptic. Gauze packing with iodoform is used in medical applications. However, the antiseptic properties are due to the liberation of free iodine, not the dry iodine molecule itself. Due to iodoform's penetrating odor, other antiseptics are used more commonly. Carbon tetrafluoride or tetrafluoromethane is a clear liquid with a sweet smell. Carbon tetrafluoride has a variety of uses, including in the manufacture of refrigerants and aerosol propellants. It is used in the synthesis of fluorofluorocarbons. It is widely used as a solvent. Due to safety concerns, many chemists prefer to use other solvents. In the past, carbon tetrafluoride was used as a dry cleaning fluid, a degreasing agent, and spot remover, and also as a fire extinguisher. These uses have been generally phased out to minimize health risks. The health risks associated with carbon tetrafluoride are very serious, as the substance is a suspected carcinogen. Chronic exposure to carbon tetrafluoride may cause liver cancer in humans. Kidney damage is also a risk. The side effects of exposure to carbon tetrafluoride include dizziness, lightheadedness, nausea, and vomiting. It causes eye irritation and may lead to an irregular or stopped heartbeat. Continued exposure can lead to unconsciousness, coma, or even death. Carbon tetrafluoride has been linked to the depletion of the ozone layer. Depletion of the ozone layer increases our exposure to ultraviolet light, leading to a high risk of skin cancer, eye diseases, and disorders, and possible destruction of the immune system. Freon is linked to a class of compounds that are chlorofluorocarbon derivatives of methane and methane. These compounds are extremely stable and unreactive. They are non-toxic, non-corrosive, and easily liquefiable gases. Freon 12, illustrated here, was one of the most commonly used freons in the industry. It is manufactured from carbon tetrafluoride by the Swartz reaction. Former uses of freon 12 include aerosol propellants, refrigeration, and air conditioning. Since 1994, the use of freon 12 has been phased out according to the Montreal Protocol due to environmental concerns. Freon 12 and other fluorofluorocarbons are known to initiate radical chain reactions that lead to the destruction of the ozone layer. The final compound that we discuss is known as DDT. Paul Mueller was awarded the Nobel Prize in Physiology and Medicine in 1948 for his discovery that DDT could be used as an insecticide. DDT has been used to prevent insect-transmitted human diseases such as malaria, spread by mosquitoes, and typhus, spread by lice. However, many insect species develop resistance to DDT, limiting its effectiveness. DDT is toxic to many species of fish. For certain species of birds, such as ospreys, eagles, pelicans, falcons.
DDT is stored? The DDT is stored in the fatty tissues of the body and is metabolized very slowly. So must remember this line, and the structure of DDT is also very important. Very important part of this chapter, polyhalogen compounds, when we are dealing with the structure of DDT and DDT use. You must have dealt with this chapter in a very good manner. You must have completed all the questions simultaneously as we were doing together. Must do the conversion part, because a number of times students find difficulty in doing the conversions. So must complete the conversion part here. Some of the important questions of conversion. Must remember the back exercise question. These are question number 11, question number 14, question number 19. Very, very important. So do these questions simultaneously.
Chloroform is used as an anesthetic. It is used as a solvent and to make flame, R22. Dichloromethane and chloroform are both toxic and harmful to the central nervous system. Triiodomethane has an unpleasant odor. It was formerly used for its antiseptic properties. Carbon tetrachloride has a variety of uses. Carbon tetrachloride is a carcinogenic, freons, or chlorine.